Alan Zimmerman. As you heard, I've been working the API annotations in GHC. I came to this just to give some background. I started working on the Haskell refactor a couple of years ago. At the time, it didn't work with GHC, was basically dormant. There were some papers saying that there were fixes that had been put into GHC to support it, basically rich token streams. And yeah, I thought, okay, let me tackle this. Spent far too much time on getting it to work with a token stream. There's an immense amount of fiddly stuff to actually get anything done, and you've got to tie it up to the AST, tie up the token stream, find the actual keywords that are missing everywhere, and a huge amount of problems. And the main issues is that it's one thing to kind of tie the token stream to the AST, but as soon as you try and change anything, then the tokens are absolute. So you have a row, you have a column, that's where it's going to come out. If you change anything, you've got to rework all of them. If you want to change your indentation, you've got to go through everything and work out where it is. If you want to add a declaration somewhere, you've got to make sure that the layout rules are followed. It's all immensely complicated. And in writing your actual refactorings, you do 1 or 2 lines of updating the AST and then 40 lines of messing around with tokens. So it's basically just not practical. So I had a look around at what the Haskell source extensions guys are doing. They had this cool thing called ghc-exactprint, which kept track, in their annotated AST, kept track of the locations of all the non-terminal items in the AST, the lets and the ands and the wheres and the do's and things. But it suffers from the same problem of the token stream in GHC's AST, in that you're still fiddling around with very exact locations. To change any one part of it, you've got to pretty much change everything. It was the same problems we had with the tokens. But at least you didn't have to mess the tokens. You could work with the AST, so it's a step in the right direction. So I decided to take a 2-step approach, put in the similar API annotations as in the Haskell source extensions, but then write a second step that would turn those absolute locations into relative ones, so that it could then, essentially thinking of a pretty printer type model where you say this is so many across, or this is above that, or whatever, end up with that sort of situation. This was around about the 7.6 time. The plan was to first of all get rid of the landmines that were in the AST at the time, because there was this brilliant idea of, if you try and use a field in the AST that is in its wrong phase, you try to use a type when working with the power source, it'll blow up with a nice error, so you know you've done that, and as a compiler writer, that's great. As someone who's writing transformations on the power source, that's not such a good idea. And then add the actual annotations was the next step. And the other thing which popped out of the woodwork, which I wasn't expecting, was the original source literals were not actually being properly captured. So if you had a string that had Unicode escape characters in, the string the compiler saw is the one with the Unicode character in it. If you reproduce that source code, you need the original escaped text. So there's lots of little wrinkles of that nature. So you may have noticed there was quite a lot of work done over the last however long. It's now it's in 7.2. Matt Pickering has used it to round trip most of Hackage. There are a couple of things that don't fully round trip. We know what they are. It's to do with things like multi-line strings in Pragmas. And there is a fix in head, but they're going to be, it didn't make 7.10.2. The approach basically to sort out the landmines, we brought in the post type checker and the post rename type families. They essentially, the post renamer only has, when you're working with a parse source, it's a placeholder, and after that it's the type you need. Likewise for the type checker, so this means that you always have a safe AST. You're not going to have any landmines. You can iterate over it cleanly. The API annotations themselves, this is now part of GHC, introduced the structure, which is, it basically just identifies what is a specific keyword we're talking about. The keywords are tied to a source span. So note if you have a let expression, then the let keyword will be tied to the let expression as a whole. And what comes out of the parser, if you turn on keep raw token stream, is this, which is a map of the keys to the actual source spans that these things take up. It's a list because, for example, semicolons, you can have a lot of them in a row. It also brings out the comments tied. Each comment is tied to the lowest enclosing source span. So instead of just being one lump at the end, it's actually located as tightly as we can at that point to the element that it belongs to. That allows us to do this. Anyone who's worked on the parser will have seen a huge amount of extra noise that's appeared in it. This red stuff is what I put in. So essentially, when you have a do statement, we add the and do, which is this MJ is a little utility function. Heaven knows why it's called that, but that's how it is. It probably needs to be renamed sometime. This add and thing is basically a lambda. You give it the source span where this thing must attach to, and then it adds it into that structure that comes out. So it's simple. You call AMS, which does a monadic add of a list of annotations to a production. So you need the percent there, and essentially you pass back what would have been the return. But in this case, because statement list has its own annotations, which need to be passed up, that comes up as a tuple. So the AST is built on the second, and the annotations come out as the first. And with this mechanism fully worked through in the parser, when the parsing is complete, if you've turned on the keep raw token stream, you're going to get these annotations out, which you can then use, and which is what we use. So here's an example. If you parse this code, this is a dump of the actual annotations. Here the and do is tied to from 2.7, which is there. So I've got the shakes down to 4.10, and the location is line 2, column 7 and 8, and the let is a expression at that level, and it's tied to 3.3 there, and that's what its locations. So this is what you now get out of the parser when you use it, and this is now equivalent of what the Haskell source extensions guys have got, except that it's indexed by that rather than being just this array, and you've got to know where they live. The next piece of the puzzle is a separate library called ghc-exactprint, inspired by the Haskell source extensions exactprint. But the changes are, it has to allow changes to the AST, and the changes need to be local. And also, it can't depend on the source span. So those annotations are, the source span is used as an index into the structure, but that's all it's used for. I'm talking about in the ghc-exactprint world. Once that's done, it is used purely to link the two together. After that, it has no meaning. So if you add areas into the AST, if you take pieces out, it doesn't matter. You're not trying to relocate everything beyond it. And it also, so that gives you these edit operations that are not dependent on that. It also automatically manages the layout rules. It knows where layout applies. If you make changes, it's going to line the layout out as you do it.
It's telling us the differences from Haskell source exactprint, but we don't know what that is.
Okay, the Haskell source exactprint is, they have an annotated AST.
Just tell us what your one does. Rather than by telling us a diff.
Okay. I'm going to do it now. Okay. This is modeled on a pretty printer, as I said before, where essentially each annotation, the ghc API annotations are converted into ghc-exactprint annotations, which are then essentially saying this goes above this, this goes next to that. So you have completely local operations, which can then, any changes are made locally and they have a global effect if they have to, in terms of changing indentation or things like that. And it's a separate library from the Haskell refactorer because I'm pretty sure it will find more general use. In fact, Matthew Pickering has used it as a GSOC project to apply the hints from HLint successfully. Runs in 3 phases. The first one takes the ghc API annotations and converts them into this relative format. There's then a transform library, which is under heavy development at the moment. We're still feeding our way around how precisely it should work. And then the print stage will recreate the source code, possibly transformed. The test we've done is to just do delta and then print, and it comes out as original. This is what the ghc-exactprint annotations look like. We also have our own keyword ID where the first one just wraps the ghc one. We also have some other specific ones. Sometimes we need to know specific roles that a semicolon plays because they're quite tricky in the thing. We sometimes need to take the comments and put them in line with the token stream when they are, if you've got an inline comment in your code. This and string, we need to deal with some funnies that happen from time to time, and hopefully we can get rid of it one day. And this is where it is a Unicode character. The fact that it's a Unicode character in the particular representation is lost. So that's basically a standard ghc keyword ID, but we say it is Unicode as well, so we know to deal with it. The other change is that the key that we use to look these things up with is now a source span and the constructor name. Basically, the AST will sometimes have elements that share a source span, but the one is nested inside the other. We need to make sure that we work at the right level of the AST when applying these annotations. And the annotations then are just a map from the keys to the annotation. The annotation itself is all of that. Now, the first 3 fields deal with the local context. That defines the top left point of the annotation, the piece of the AST being annotated. If you set the top left point, everything below that will just flow off as expected. And that gives you your complete relative location. So you can take a piece of the AST, plug it in somewhere else, provided you set the top left point, it's going to flow through. The entry delta, the generation of output works on the concept of an output point, and that delta there just says from where the last output happened, go forward so many rows, so many columns. Prior comments are any comments that come before this particular item, and following comments are any comments that come after it. They're also just treated as things to go out, and so if you change the entry delta and there's prior comments, you may have to do a little bit of fiddling, but there are, in the transform library, manages that for you. And then going down, this is the heart of the thing. That's just the mapping of the keyword ID to a delta pos. So for any given piece of the AST, there's a set of, for the delta and print operations, there's a set of, it essentially works through it, says, okay, this is a let expression, I expect to find a let annotation. So put it in or print it out and so on. So it's just used to apply those. This is an interesting one. In order to use the source span just as an index, you cannot use them as a sort order. If you delete things, if you add something, if you move something from one place to another, you need to get the order that you intend having. So that is captured in here. It's essentially, and those source spans are used purely as an index into the sub-elements of this particular one and captures the order that they need to appear in. This means you can add new elements with, construct a completely fictitious source span. So long as it's in here, it's going to work. And this captured span is for when you're working with radar names which have got annotations on. There's a bit of a workaround, but it just eases things through. So if we take the previous example, it gets converted into this. First of all, the do is one column to the right of the equals, so the entry, the DP is 0, 1. There's no leading comments, no following comments, and that's all it needs. The let statement is 1, 2 down, so we go one row down, 2 columns across, and that 2 nests. So if this thing was then moved lower down in the AST, that 2 would just be added to whatever we had before. The actual let expression, the fun bind there, you'll see there's a gap across there. It starts 4 characters across from the let. So this is now this is what ghc-exactprint uses. These are the annotations that are now completely relative, which means if you make changes to the AST, then you can print it out again and it will still work. So out of the box, if you take that expression and you replace this name with a longer one without changing annotations at all, it's just going to push everything out. Layout will stay the same, everything will just keep where it was. That looks simple, but it's very difficult to do using any of the others. The transform library provides a monad, and that basically just manages the annotations as you update them, and it just keeps a simple counter to give you a new source span if you want one. And because the source span uses indexes only, it simply gives you just a sequence number that runs up. So you can get a unique one. And because because this is just an index, you can add and remove source spans. It's just a tie-up point. And there's some operators to simplify modifications. One of them is this class has decals. If a given element has sub-declarations, you can just say, give me the declarations, and it'll give them to you. And then when you replace them, you just give them back, it'll put them back. So, for example, if you have this function, and you call replace decals with that nn equals 2, it'll automatically add the where clause, the where keyword, because it knows that that's required, and sort out the indentation and so on. So you don't have to worry about stupid things like, and if you put back an empty one, if you go from there to there, it'll do the same thing. The where will disappear. There's also, in order to plug it into other monads, there's just a simple has transform which will lift it into that, which I use to integrate it into the refactoring monad in the refactorer. Here's an example of code from the test suite. If we start with this, where we have that declaration there, if we simply do it, okay, in this case, we don't have to worry about it. We can match on every single let we find because there's only one, and it's a test. We requested declarations, we put them back, but we drop the last one, and it goes to that. So really simple, no fiddling with tokens, it just does what you expect. Matthew Pickering wrote a blog post some time ago, I'm not sure how many of you saw it, this thing, the identity transformation. If you're writing tools that are changing code, you need to first guarantee that the original code gets preserved and only the changes come through, so you need to be able to do the identity transformation. So Matthew Pickering has been working with me on this. He did his Google Summer of Code project on HLint, but also working on ghc-exactprint. And he was actually doing it long before the Summer of Code project and has done some awesome stuff. But he regularly round trips it on Hackage. At the moment, he runs on a Mac. There's a problem with Clang and CPP. We have a workaround for CPP, but it only works for the simple stuff like hash if and whatever, where it essentially turns, our initial phase turns the non-active C++, CPP code into comments, which then just work through as normal comments and I'll take them. Obviously no transformations will happen in them, but it can round trip CPP code so long as it's not too complicated and you're not running on Mac. But I think there can be workarounds for that. Silly things, multi-line string literals in pragmas, we know about, there's a fix in head, it must come through. The Unicode is a workaround. We know that at the moment it needs to be dealt with as a first class thing. At the moment it reduces a 2-character item to a 1-character one. We can pick up, we know it's there, and we can deal with it. Star becomes a star, and we can't take that round. So I think going forward we want to make that a first class representation rather than just hacking it through. Now, an example is there's a library Apply-refact that Matthew Pickering did for his Google Summer of Code. It's on Hackage, and I can show you how it works. So here we have you'll notice that's an HLint hint that says we've got this very complicated if then else, why not do that? So we can say, okay, let's do that. And there we go. Just like that. And likewise, we can say, okay, we have a redundant do, and oops, does that as well. So, it's there now, it works. It needs to be properly integrated into various bits of tooling. The Emacs Haskell mode guys have undertaken to do that. There is a Vim integration of it as well, but both of those are more proof of concept than really robust. Okay, and that's me basically done. There's various other things that are going to happen going on. One of them is I'm hoping that now that we have, as tool writers, we've kind of staked a claim on the parse source and the ghc API, and we've got rid of the landmines. I'm hoping that more people will start using these things, which means that when changes happen in the compiler, the tool writing community are going to be involved in that process, so things will evolve to support just straightforward compilation as well as tool-based compilation. Things like the parse source, you don't have, the renamed source is different from the parse source. You can't use it for doing the transformations. You can't actually round trip it. So you have to look up if you want to work with name-based stuff, you've got to look them up. And at the moment, there's this messy process of going from a located radar name to an actual name, but not every name is located, so it gets messy. So that's one of the things I want to do. I want to see about perhaps making the renamed source more closely match the parse source, so that you can actually do transformations on that. Alternative to this is to make a lookup table somehow that we can tie the name in the parse source tree to the name after the renamer, and more of that. And okay, that's where the ghc-exactprint lives, that's where the refactorer lives, that's where Apply-refact lives. That's Matt's Summer of Code project, and that's his round-tripping one. I'll make this available when I'm done. Okay, any questions? Say again?
Which Emacs mode was that?
That is just standard Haskell mode. Okay. And there's what Matt Pickering has done is he's written so the pop-up showing the hint is part of Haskell mode as it stands now. Okay. That's just Spacemacs out of the box install, not doing any particular tweaks. And then if you take, there's an Apply-refact mode for Emacs, which you install as well. You have to install it from the repo. But all it does is puts the commands in that actually do that apply the hint.
Great, thank you. But the other question I had attached to that was, is the guarantee for Matthew Pickering's tool that it never changes the semantics of your code?
His tool only applies the hints that come out of HLint.
Okay.
So you're asking the wrong person.
In practice, like, I don't know if you fuzz tested that by applying it to all packets or whatnot, but are there any scenarios where the results are found any corner cases related to like
That's something that's on the list. The idea is to run through stackage, make the changes, and then be able to compile it again. Because running through hackage as a whole, you obviously have the problem of just, does the stuff actually compile right now? Because can you configure it? Can you get your cabal macros.h to pop out and all these other hairy problems that you get? So the idea going forward is to run through stackage and see that that does in fact happen. Yo.
So would you recommend this as do you think this approach is good in general for a syntax tree? I mean, say, for example, people have trouble that you can't do edits to val files, for example, layout commands. Should we be doing it this way?
Well,
Or simpler ways? What would you recommend?
I think that the approach in ghc-exactprint of turning everything relative is completely general. The same source information is available in, for example, Haskell source extensions. I'm pretty sure that a variant could be put together that will do the same thing there. And likewise, if you have the same information in a Cabal file, yes, you should be able to do it there as well. It's a general approach of essentially, my mental model is returning the annotations into pretty print directives, which means you can then move things around and get it to work. In fact, I took a long detour through when I was working with the token style. I ended up using the dual tree from diagrams, which deals with a very similar problem and allows you to accumulate your structure from the bottom coming up, applying constraints, which is quite useful.
Yeah, so I have a question, which is how much sort of flexibility do you have in the actual construction of the nullifying graph? I imagine there's like different ways you can decide to nullify something, which means that when you edit it, it's inconsistent, right? There might be multiple natural ways of adjusting code.
I don't think there are really that many places, because the annotations, at the end of the day, it's about the scope of where the thing arises. So there's normally a very clearly defined point where the particular keyword needs to attach, and the approach is to provide output relative to the previous output point. And if you take those two constraints into action, then there's not a lot of freedom for it.